First off, I just wanted to thank TTI and Texas A&M University for putting the short course program together. They do a great job, just like they do every year. Also, I wanted to thank the design folks for giving me this opportunity to present on the I-35 NEX project on behalf of the San Antonio District. It's a very important project to the district. Kind of my role in this project is I'm the project manager. Currently, I am managing the schematic environmental effort on one front, kind of on another front. I'm serving a role as working on the design build procurement. And also I'll get to follow this project out into the implementation phase as the implementation engineer. So it's kind of cool to get to see all the hard work in the front end kind of come to fruition. It's kind of next slide is just a presentation outline. So kind of the focus of this presentation will be more on the design aspects of the project and kind of some project history. We're really not going to get into the design build aspect of the project. And as you can see on the bottom of this slide, there's a disclaimer. Currently, we're in an active design build procurement, so any topics specific to the procurement won't be discussed. Also, I won't be answering any questions specific to the design build procurement. So getting into the location of the project, it's of course, in the San Antonio District. The project location basically traverses 3 counties. It goes through Bexar, Guadalupe, and Comal County. It runs through a very highly urbanized, congested I-35 corridor for a majority of the project. As you can see, the project limits begin on the south end of the project near AT&T Center Parkway, almost in downtown San Antonio. And they run all the way up onto the north end, up into Comal County, up to FM 1103. I do kind of want to point out that 410 and 35 kind of run as a dual designation through this area. So the interchange on the south end we call 410 South. This is a 410 North interchange. The project proposes improvements at those 2 interchanges as well as the Loop 1604 interchange. So all in all, it's roughly a 20-mile project, and that's not including the interchange runouts. Whenever you add those in, it's roughly a 25-mile project. The goal of the project is kind of to get the longer origin destination travelers from the northern end of the project up in the New Braunfels, FM 3009, FM 1103 area, down to the 410 commercial developments in the airport area, and to the downtown employment centers. And one thing I don't have on the slide, the design build cost of the project is roughly $2 billion. So on to the next slide. As you can see, kind of the population trend. It's a highly congested corridor, as you can see. A lot of population. Population is expected to continue to grow up through the 2045 planning year. So on to the next slide. So building on that population growth, it's very inherent when you have population growth, you're going to have traffic growth. So the top left graphic kind of shows how the project has been segmented into 4 different segments based on traffic characteristics and based on combination of several different sources, including historical data, travel demand models, TIAs, et cetera. We're able to come up with growth rates for the corridor. So the top right graphic kind of shows what those traffic projections are going to be for the design and the future years. One thing I want to note, the total traffic is, if you add the main lane and the elevated lane traffic numbers together, that's the total traffic for the corridor. So in some locations, we're pushing 400,000 vehicles per day in one segment of the corridor. Bottom left is just a typical peak period congestion screenshot. If you ever drive on 35 during a peak peak period, you know that you'll be sitting in traffic. The bottom right is basically a Google Earth traffic screenshot taken. It looks like this is probably taken in the PM peak when all the traffic is trying to get back out to the suburban areas. So now getting into the project history, a planning and environmental linkage study, or a PEL study, was completed back in 2013. Basically, this PEL study developed the need and the purpose for the project. It took a pretty detailed traffic study, and as you could see on the previous slides, it basically concluded that there's inadequate capacity on 35. So the recommendation from the PEL study was to add capacity to 35 and improve and connect the I-410 South, the 410 North, and the Loop 1604 interchanges. Also, one of the main things that came out of this study was it analyzed some of the impacts to the right-of-way if we were to expand at grade. So basically took a look at the fully developed right-of-way, and it's really infeasible to expand at grade. We'd be wiping out pretty much all the businesses along the corridor. So the recommendation was to build the added capacity through elevated lanes up to, on the northern end of the project, up to around FM 3009. Through there, we have a little bit of additional available right-of-way. We're able to expand at grade from 3009 to FM 1103. So continuing the PEL study to the next phase, schematic environmental study was completed back in 2015. The schematic environmental effort pretty much proposed 2 toll lanes in each direction, as you can see on the graphic at the bottom, and it configured the tolled managed lanes as elevated lanes between the main lanes and the frontage roads. The project was environmentally cleared through an EA. The FONSI was issued back in 2015. So right around that time, or just shortly after environmental clearance, there was more of a statewide direction to move away from toll projects, coupled with a lot of public opposition to the project. The toll component was eliminated from the project. One really fortunate thing that came out of this effort was that since we did receive environmental clearance, we were able to move forward with some right-of-way acquisition. Fast forward to now, there was a reevaluation that was completed just recently. So updated traffic studies basically showed the need for an additional elevated lane in each direction. So that additional elevated lane is an HOV. So the elevated lanes consist of 1 HOV, 2 general purpose lanes in each direction. Basically the purpose or the thought behind the HOV lane is to provide flexibility in the future for if we were to do anything innovative like a autonomous vehicle lane, bus on shoulder, anything else that we might come up with in the future. So the scope, of course, included building the elevated lanes and also retaining a majority of the existing I-35 capacity and access. So that was a major component, was that we're basically building the elevated lanes on top of the existing facility. The EA reevaluation was approved just recently last month, September 23rd. So moving on to some of the project challenges that we faced and are currently facing. We're having to purchase some additional right-of-way. We've got utility impacts, basically, as almost any project has. We were able to minimize the right-of-way acquisition. We were able to employ single column bents for a majority of the project, but as you can see the graphic on the left-hand side, anywhere where we had to straddle a ramp, straddle a frontage road, we had to place multi-column bents. Whenever you start impeding on the utility and drainage corridor between the frontage roads and the existing right-of-way, we have to have a place for the utilities to relocate and for the drainage ditches to be graded out. So a majority of the right-of-way acquisition is because of that case that I just described. So there's a total of 80 parcels and about 15 acres of additional right-of-way that we're looking to acquire. And since we were able to get environmental clearance, we've done a lot of the prep work on the environmental, like obtaining the legal descriptions, getting preliminary appraisals, right-of-way mapping, et cetera, kind of behind the scenes, so that we're able to go ahead and offer for the right-of-way acquisition now. Getting into the phasing of the projects. So the project has been broken down basically into 3 phases: Base Central, Base South, Deferred Work Component North, and these are mainly for design build purposes. But the Base Central and the Base South project are currently funded. The Deferred Work Component North is anticipated to be funded in the 2021 UTP, but currently remains unfunded. So we had to come up with a plan on how to phase kind of that interface between the base project and that unfunded Deferred Work Component North. So this next graphic kind of shows graphical representation of how we've phased the project. So the base project, which is what we would call the interim project, builds everything that you see in light blue. So the elevated lanes coming up to where the stub out locations would be built in the base project. We would drop a ramp down to connect to the 35 main lanes in the northbound direction, while maintaining the clearance over the future elevated lanes that's kind of in the orange color that you see. That's part of the Deferred Work Component North. So we're able to build the base project and accommodate the Deferred Work Component North project with very minimal throwaway in this area. Also, I want to point out, currently a design exception exists for this area through I-35 for 11-foot lanes on the main lanes. So as a part of this effort, in order to run out the ramps that connect to 35 main lanes, we're having to widen some of the bridges. In the future, whenever the Deferred Work Component North elevated lanes are built, we'll be able to eliminate that design exception because we'll be able to restripe the exit ramp and the entrance ramp up onto the elevated lanes as one lane ramp. So we'll be able to get rid of an existing design exception out there. And this is just kind of a graphic. It may be a little bit difficult to read, but it's of the schematic. So you can see in the northbound direction, base project would build up to the stub out location and then bring this exit ramp down and connect to I-35 while accommodating the northbound elevated lanes. So since this is primarily a structural project, the project consists of roughly 45 linear miles of elevated structure. That's linear miles, that's not lane miles. So basically 45 miles of 3 lanes in each direction, elevated structure. So the schematic was designed using kind of what San Antonio District knows as tried and true, traditional hammerhead type columns, inverted T bent or caps with TX girders. However, we're not precluding any innovation with the design build contract. Also, it does not preclude any precast or segmental type construction methods. Straddle bents were employed where some of the column eccentricities exceeded the hammerhead cap design limits. There are some areas at some of the interchanges where we're having to employ really long steel spans at some of the direct connectors. Some of them range in the 350 foot. So also clearance requirements were kind of a problem over some of the cross streets and interchanges, having to accommodate the the 18.5-foot freight corridor clearances that we're required to do. And then also provisions are going to be included in the design build specs to not preclude any future direct connectors at interchanges such as 1604. The eastern direct connectors are not included as a part of the design build project. Also, we took a look at some of the future cross-street expansions, what we can do in those areas. So we're accommodating those with our bent locations. We're setting up those envelopes to not place any bents in some of those future cross-street expansion envelopes. So this is just a screenshot of the Open Roads 3D open bridge model. It basically just kind of illustrates some of the complexities that we're looking at the Loop 1604 interchange. One of the really long spans that we're looking at basically is these spans here at 1604. We're looking at more in the 350-foot range. So some of the roadway and the geometric aspects of the project were somewhat challenging. By having to add the additional lane from the 2015 toll project and try to incorporate a 10-foot outside shoulder, basically we would have to employ the straddle bents along the full limits of the corridor, and that was going to create huge right-of-way impacts. So we were able to reduce that inside shoulder to 4 feet. Adjacent to the HOV lane. It doesn't require a design exception, but we were able to save a lot of right-of-way acquisition through doing that. Some of the design exceptions that we will need on the project, they're pretty minor. One of them is reducing the shoulder widths at the ramps, where we're having to straddle the ramps and add SSTR to protect those columns. We'll be reducing those shoulder widths at the ramps. Also, the bents, some of the bents at the interchanges will be placed in the center of I-35, so we'll have to do design exceptions to bubble out, reduce those shoulders at those median bent locations. Also, as I mentioned earlier, the 11-foot auxiliary lane in the interim condition, that'll go away whenever we build the northern deferred work component, continue the elevated lanes to the north. We'll be able to restripe and eliminate that design exception. Also, trying to shoehorn in the direct connectors was kind of challenging to get the vertical and horizontal geometry to work. And there's some areas where, in order to shift traffic for traffic control purposes, we're going to have to improve some of the shoulders that were not built to the same pavement structure as the rest of the main lanes back in the day when it was built. Also, I don't have it on the slide, but one of the challenges was to provide ped accommodations on the existing frontage roads. A lot of the existing frontage roads currently don't have the ped accommodations, so we're looking at filling in a lot of the gaps and upgrading ped signals, ped ramps and all that as a part of this project. So this is just a graphic kind of showing what I was talking about as far as having to straddle some of the ramps with straddle bents, employing design exceptions in that area where we're having to add the SSTR, reduce that shoulder width. This is a graphic that kind of shows what the typical section would look like if we had to employ the 10-foot outside shoulder. For a majority of the project, we'd look at having to straddle the frontage road rather than using the single column bents. So one of the other challenges we had was the drainage approach. So basically, how do we get the water down from the elevated lanes, pipe it down to the nearest outfall? So one of the challenges was to basically retrofit the existing drainage system, or the proposed drainage system, into the existing system. We had to evaluate each cross structure to make sure that it could handle the additional queue. Some of them could, some couldn't. We had to make some improvements to some of the cross structures. Also, it's just the cross-sectional space. We're having to employ a brand new trunk line to bring the water, to pipe the water from the elevated structures down to the outfalls. So it's a very congested cross-section with utilities, drainage, whatnot. So it was we had to be somewhat creative in getting that trunk line to fit within the cross-section. Also, capturing the runoff, how do we capture it? We're proposing to place inlets basically at each bent in order to meet the ponded width requirements. This is kind of where the 4-foot shoulder is somewhat of a drawback in some of those super elevation transition areas. We're only able to pond the 4-foot shoulder rather than having a 10-foot shoulder for ponding widths. So there were a few locations where we needed to add intermediate inlets even between bents. And that was kind of a challenge on how to incorporate that drainage system into the proposed drainage system. So also we set up our hydrology to account for future development kind of on the north end of the project where it's not overly developed. We wanted to account for that future queue coming into our system. And then also Atlas 14, we experienced some of the higher queues on some of the lower frequency storm events. We had to mitigate, but we were able to mitigate those. The next slide just kind of shows kind of what the column configurations look like and how we're capturing the runoff, piping it down the columns and outfalling it outside the columns. Another challenge to the project was public involvement. So the San Antonio District really employs a proactive, transparent approach to public involvement, and especially on a project of this magnitude that previously received a great deal of public opposition when it was a toll project. So our goal was to be as transparent as possible, to educate the public with the correct information, since of course there's always a lot of rumors floating around. So we conducted stakeholder meetings with all the local entities, all the local municipalities, EMS, major business owners along the corridor. We met with affected property owners, anyone who we were acquiring right-of-way from. We gave them the opportunity to meet with us. And then also the public hearing was held back on August 15th, 2019. It really ran very smoothly. We got a lot of positive public feedback, and primarily it's because the toll component was removed, and we're really not impacting people's local access. So everybody was happy. This is just a graphic from our public meetings. So kind of the way that we do our public hearings in San Antonio District, we do a 1-hour kind of open house type setup for an hour before. It really works well to interact with the project, kind of explain the project to the public and receive feedback. And a lot of the questions that people have are answered during this open house period. It really helps kind of with the flow of the public hearing. So this is just a graphic showing kind of the development along the corridor over the years. Top left was taken, I think, in the 1960s. Bottom left is what it looks like today. And the graphic on the right is what it's going to look like once this project is built.